All right, college algebra class, these are the notes for section 3.5, last section in chapter 3. Again, we're going to be looking at transformations of graphs. So vertical shifts, horizontal shifts, stretching and shrinking both horizontally and vertically, and reflections over the axes. So we will kind of break that down and how it looks with seeing those transformations as they appear into basically generic type of functions. Okay, so many times when we demonstrate these transformations, we'll use one of our basic parent graphs. Many times it's a parabola, but maybe we'll use a square root function, maybe an absolute value function. Those all work nicely for demonstrating these different transformations. Okay, so right away it says, for vertical shifts, I think these ones are pretty easy to recognize because what you see is pretty much just your parent function, and then you'll see a constant either being added or subtracted after the main parent function. And so basically all that does is it adds that value, or subtracts it if it's subtracting, to each y coordinate. So if this blue parabola is my parent graph, y equals x squared, then all I'm doing is adding 2 to each of the y coordinates to obtain y equals x squared plus 2. I wrote it this way just because we're used to seeing the vertex form of the parabola, which would be looking like this. So in this case, once we would graph this out, we'd know that our vertex is at 0, 2, and I was just making a comparison there. So similarly, if we started with a square root function, we would just add 2 to each of the y coordinates. Okay, for horizontal shifts, these ones maybe we got to think a little more, because anytime we have a horizontal shift, then the transformation is sort of the opposite of what we see in the equation. So for example, if your x in your parent graph gets replaced with x minus 2, that indicates a shift to the right, which is somewhat the opposite of what we might think. But yeah, so that's, an x minus 2 would be shifting each x coordinate right 2, okay? And so they give a couple of examples, and we know, like when we do the HK for the vertex, when we have it in vertex form, we always take the opposite of the value that's in parentheses like that. So we know that this is shifting it right 2, because my vertex in this case would be 2, 0. Similarly, with a square root function, it would work the same way. So these would be right shifts when we replace our x with x minus 2. And then if we replace with a plus, right, that's shifting it to the left. So if I have x plus 3 rather than x in my function, whether it's a x squared, a parabola, or a square root, then that's going to shift it to the left 3. So every point moves left 3 then. If my parent graph is here, I'm shifting every x coordinate 3 to the left. So for horizontal and vertical shifts, when we make just comparisons in general, so regardless of whatever the function is, if it was x squared, we'd have x squared plus our constant. If it was square root of x, we'd have square root of x plus our constant. But the key for a vertical shift is that you don't have the parentheses around it, right? It's just the original function and then plus or minus your constant, which is going to tell you up or down. Now with the horizontal shifts, that's where we see it's inside parentheses. That constant will be in the parentheses. And so then when it's in the parentheses, then we know, oh, that's horizontal, and it's the opposite of. So this would be a right shift, and the plus c would be the left shift. Okay, so again, they might use the absolute value function as a demonstration tool for doing some of these different shifts. So, and we may have combinations, right? We might have, this is just the parent graph. This would be shifting it right 2. This would be a combination of shifting it right 2 and down 4. And many times with like parabolas or absolute values, then we have like a vertex point that we can start from there, and then we shift it right 2 and down 4, and then do our parent graph shape from there. Okay, so with this one, I sketched the parent graph of y equals, or f of x equals x squared in black right here. And then for part A, it says let's write an equation that shifts that graph left 2. Okay, so if we're going to shift it left 2, our new function is going to be x, and it's horizontal shift, right? So we need to go in the parentheses, because it said left 2, and then we'll go plus 2 and then square that. So x gets replaced with x plus 2. And then if we graph that, we're going left 2 with each of these x coordinates. Left 2 on the vertex, left 2 for that one, and each of these, 1, 2, 2. Okay, so then we get a parabola that looks kind of like that. All right, and then for part B, it says write the equation that shifts it both left 2 and down 3. So for part B, we're going to go with the first part's going to be the same. Our left 2 is going to look like this, and down 3 we have to subtract 3 from that. So now we've already done left 2, now we're going to take each point, drop it down 3 units. That one there. And right there if we drop that one down 3. So that would be the combination of the vertical and horizontal shifts. Okay, so vertical stretching and shrinking. Okay, so this would be like, in our parabolas when we have the A value out front that makes it, a skinnier parabola. That's, for example, here. Basically, all we're doing when we have vertical stretching and shrinking is there's a coefficient that's in front of the the function itself. And so all it does is multiply the y-coordinates times whatever that A value is. So if you get an A value bigger than 1, that's going to give you a vertical stretch, which is like what's happening here. My parent graph is the square root of x. If I multiply each of those y-coordinates, the x-coordinate stays the same, but I multiply the y-coordinate by 2, it's going to stretch it vertically. Okay. If I have a number that's between 0 and 1, then that's going to be a vertical shrink, and it'll kind of squish it flatter, right? So like where the y-coordinate was 1 here, now it's 1/2. Where it was 2, now it's 1, so it makes it flatter. It's a vertical shrink there, okay? Okay, horizontal stretching and shrinking. Any of the horizontal transformations, whether it's, shifting left or right, or if it's horizontal stretching or shrinking, anything that's horizontal transformations kind of has the opposite. You got to be thinking opposite effect in a way. And so what I mean by that is, so within the function itself, if you have f of 1/2 x, so if it's inside the parentheses and multiplied by the x in there, then what that means is that you actually are multiplying all the x coordinates by the reciprocal of whatever that coefficient on your x's would be. Okay, so it's not out in front of the function. It's not just multiplied by the whole function itself. It's each x in the function is multiplied by something. And what that does is actually has the opposite effect. So if I have a 1/2, I'm actually multiplying all the x coordinates by the reciprocal of 1/2, which is 2. So in this case, I would multiply x coordinates by 2. And that's how I would get from my parent. This is just like my parent graph. It's just a line graph, but they're just using it as an example. If y equals f of x, and they've got these ordered pairs, which is just a dot-to-dot line graph. So where the x coordinate before was -2, if I have f of 1/2 x, that x coordinate now becomes -4 because I multiply by the reciprocal of 1/2. Okay. So multiply x coordinates by 2 in this one, and in this one, you're multiplying the x coordinates by the reciprocal of 2, which is 1/2. And so here where I had -2, that's -1. Where I had -1, that's -1/2, and so on. And so you can see what that does is that this distance gets cut in half. It's a horizontal shrink. Whereas here, this distance gets doubled, and so that's a horizontal stretch. So think anything horizontal transformations, you have to kind of do the opposite of what you think. So like when it's translating left and right, if it's a minus, it actually goes right. If it's a plus, it goes left. And when it's horizontal stretching or shrinking, you got to think I got to multiply by the reciprocal of these values. So we'll see some more examples there. Okay, so they do like to kind of just use these line graphs, like just some random ordered pairs that are connected dot to dot to demonstrate some of these transformations. So in this example, they have a 3 in front of the f of x, and so hopefully we recognize that this 3 means that we're going to be vertical stretch on that. And so I'll just write the note. So what we do here is we multiply all y coordinates by 3. All right, and I'll do this one. I'll redraw it in blue right here. So each y-coordinate by 3, right? So when I do that, I'm probably not going to be able to fit, it looks like, on here. But so this y-coordinate of -2 would have to go down to -6. 1, 2, I'm going to estimate that's about like down here. This y-coordinate right here of 1 is going to have to go up to 3, which would be here. And this y-coordinate of -1 would go down to -3, which would be right there. All right, and then we'll connect that. I have a tool to do this. Okay, so we'll just go dot to dot like this. And what I've drawn there, that represents 3 times f of x. Okay, so that's our vertical stretch by a factor of 3. All right, so do it by multiplying the y-coordinates by 3, because that 3 is in front of the f of x. Now this one is telling us, all right, it's inside the parentheses. This is going to be a horizontal transformation, and because it's a half, I'd multiply all x-coordinates by the reciprocal of that, so it ends up being a horizontal stretch. Okay, so I'm going to write myself a note here. Multiply all x coordinates by 2, because we do the reciprocal. We do the reciprocal of that. Okay. Any horizontal ones, you got to remember to kind of do the opposite. All right. So I'll do this in. Let's do this one in red here. Okay. So we're multiplying x coordinates by 2 now. So the -1 times 2 is negative. So my x coordinate here moves out to -2. Y coordinates stay the same. And I'm working with the original one that I had here. Here the x coordinate is 0, so that's going to stay right where it is. And this x coordinate of 2 moves out to 4. It's going to be out here. Okay, so then I can do this one. Okay, so I've got a line graph that looks like that. All right. So that demonstrates vertical stretch by a factor of 3, horizontal stretch by a factor of 2, reciprocal there. Okay. All right, so now we'll look at some reflections across both the x and the y axes. So when we have a reflection across the x-axis, basically what happens is all the y-coordinates get the opposite sign, and so the way you'll notice that is there's a negative in front of the entire function itself. Okay. Reflections across the y-axis are not as commonly found in most of the functions we work with, but they could be demonstrated in some of our functions, and that is where each x inside the function would have the opposite sign. And so, that basically gives every x coordinate the opposite sign. In these ones, every y coordinate would get the opposite sign. Okay, just some examples here. We can see this first one. We have, here's our x-axis. Obviously, it's a reflection across the x-axis. Sometimes they say over the x-axis, across, whatever, x-axis. Okay, this one, you can see like they're demonstrating here the x-coordinates just have opposite signs. So this is reflection across y-axis. I'm just going to say y-axis. We know we're talking about reflections here. That's a y-axis reflection. Also this one, y-axis reflection, right? All right. Okay, so for this example, again, it's a line graph, dot to dot. For the representation of f, graph the reflection across the x-axis and across the y-axis. The graph of f is determined by this table, and so I just took this, these ordered pairs, and that's where I got, those 4 dots and connected them. Okay, so what we're going to do here, and I think they're wanting us to combine these across the x-axis and across the y-axis. So at least that's the way I'm reading it. Suppose we could do it as 2 separate ones, but let's just do it as a combined. Let's reflect across the x-axis and then across the y-axis and see what it yields. Okay, so we'll have to kind of think, when we do this. So first of all, we'll go across the x-axis. So this, oops, didn't mean to erase that. This point right here is going to go across the x-axis, which is going to bring it down here, and then it's going to go across the y-axis, which is going to bring it 2 over on the other side. So that new point is going to be, so across the x-axis and then across the y-axis, that point would go there. So try to visualize that. So across the x-axis to where the upper right corner of this little square thing is, and then across the y-axis brings it right there. Okay. All right, next point right here, we're going to go across the x-axis. So since it's 3 units to the x-axis, I go 3 up above, and then I go 1 across. So that one's going to be right there. And for this point across the x-axis, since it's already on the y-axis, we really can't. Oh yeah, we can go across the x-axis, but we can't go across the y-axis. So we just go across the x-axis, and then that's all we do with that one. And then this last point right here, across the x-axis is down 2, and then across the y-axis we'd have to go 3 on the other side to put it right here. Okay, so there's our double transformation, I guess. And let's do this blue. Okay. So we would have, oops, a line graph, I guess, that looks kind of like that once we've done both our transformations. All right, and combining these together, probably the most common way that we see these combined is with our parabolas that we've worked with in this chapter quite a bit. And so, like, there was a mistake here, so this should, they said left, that should have been right. So we recognize, these h and k as the coordinates of the vertex, but really that does tell us how we're shifting, because we start at 0, 0 as our vertex on a parent graph, but if we shift it right 1 and up 3, then that's how this appears in our equation with the -1 quantity squared and +3. And then the 2 that's multiplied out front here tells us we have a vertical stretch of 2, that a value of 2. The negative that's in front means it's going to open downward, which really means it's a reflection across the x-axis. And here's our shift upward. Our k value is our shift upward. So this is just showing, starting with just x squared, and then a -1 is to the right, and then we combine that with a times 2, so that's going to double all those y coordinates and make it skinnier, and then times the negative makes it reflect over the x-axis, and then finally with the +3 at the end is going to shift it up 3. So kind of a combination of all those. Something to keep in mind, to graph a function by applying more than one transformation, there is a specific order to follow. You'll do your horizontal transformations first, and then you can do any stretching, shrinking, and reflections. Those can be done just as long as they're after horizontal transformations. Those can be done in any order. And then the last thing you would do is vertical transformations at the end, okay? And that was kind of the order that they showed these. So you do your, and that's what comes in the parentheses first, is the horizontal transformation. And then you're going to look for any stretches or shrinks, so you'd multiply next. And then you're going to do your reflections in there. Vertical transformations would come at the back end of that, the last thing. Okay, on this one it says, okay, describe how the graph of each equation can be obtained by transforming this parent graph of the y equals the square root of x, and then graph the equation. So what we see here, I kind of left the work here, but since we have a multiplier in front, that's going to be a vertical either stretch or shrink. Well, because it's a number that's less than 1, we know that's going to be a vertical shrink, so each y coordinate gets multiplied by half, but also by the negative, so by -half. That negative tells us that's a reflection across the x-axis. So there's our vertical shrink, and then reflection over the x-axis. With this one, okay, if we list them in order, the first thing we'd want to say is, okay, I've got a -2. And you would kind of think it's in parentheses that's inside of here, kind of like this, just so that we know that's all under the square root. So the -2 tells us we're going to shift right 2. Okay, the minus that's actually inside of the function, it's like f of -x. So that's where we get that reflection over the y-axis, and that's less common to see that, but reflection across the y-axis, and then at the end our vertical shift is down 1. So let's take a look at what these ones should look like if we apply those transformations in the correct order there. So I'm just going to work with, basically I've put 3, just 3 of the points from the parent graph. Square root of 0, 0, square root of 1 is 1, and the square root of 4 is 2. So I have those dots to work with. Now with this one, all we're going to do is multiply each y coordinate by -half, because that's what we have right there is a -half. Okay, so let's go red. Okay, so this one's going to stay put. That's just going to stay right there. This y coordinate of negative 1 becomes negative 1/2, so that goes down there. And then this y coordinate of 2 would become 1, and so basically it's reflected over the x-axis and it's shrunk together by, it's shrunk by a factor of half. Okay, so that's how that would look. With this one, okay, we want to do these in order now. So the first thing we have to do is our transformation, which is, this will be right 2. So I'm going to take this dot, I'm going to move it right 2, and then I'm going to reflect it across the y-axis. So 1, 2, and then I reflect it across the y-axis, which I put it over here, and then I have to go down 1, so that actually drops down to there. So hopefully you can follow that. So right 2, reflect it across the y-axis, and then down 1, puts it right there. Do the same thing with each of these other points. So right 2, reflect it across the y-axis, so that's going to go 1, 2, to be here, and then down 1 would put it right there. Okay, and then same thing with this last one. So it's right 2, reflect that across the y-axis. So what was that? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and then down 1 would put it right there. Oh, that was a little bit harder to demonstrate, but hopefully you're able to follow that. So with each of the coordinates, I took each one of these coordinates, I moved it right 2, I reflected it across the y-axis for that negative, and then I moved it down 1, and it yielded those 3 points. And I just took 3 of the, this would obviously continue on, but I'm going to just do those 3 for demonstration purposes. Okay? Hopefully that made sense. I think that is everything. Yep. Okay, so you should do your homework for the 3.5.